Okay, thanks to everybody for coming. Really great to have you all here today. And Z, thank you so much for speaking at this REALML Online reading group. So Z is a research scientist at Google Research Brain Team, whose research focuses on probabilistic methods for decision making, including lots of problems in Bayesian optimization, active learning, as well as robotic learning. Z obtained her PhD from MIT back a couple of years ago, and also I believe runs a BayesOps speaker series, which is very much in line with what we're trying to do here. So we were inspired by this. Z, thank you so much for speaking, and please take it away.
Yeah, thank you so much. I really appreciate this opportunity, and it's really nice to see that we have a reading group that has a lot of focus on the real world aspects of experimental design or like active learning in general. So I actually wasn't expecting this many people, but it's great to see everyone here. But feel free to stop me anytime. I'm just hoping to make it more interactive. All right, so when I was considering what to talk about, I realized it's a very nice chance to share some of the lessons I learned when applying like experimental design methods to robot learning problems. So a lot of the work that I'll mention in this particular presentation are things that I've done in my PhD. So since then, I don't work on robotics anymore, but the lessons here actually broadly apply to many different kinds of intelligent systems. Okay, so let's get started. We'll still take robot learning as an ongoing example. And let's think about what our end goals are for these kind of robotic systems that are intelligent and are able to like solve very complex tasks in the world. So what do we want? Different people might have different views, and the kind of things that many people would think about is just like the robots take over things that we don't want to do, right? Like things like folding laundry or cook a dinner when you don't really want to do it, and or clean up a very messy kitchen. So the hope is that we can get one robot and it just comes in and it can do everything for us. And the kind of under the like behind the scenes story there is, if we really just want one robot, then it needs to be able to adapt to new environments, and it needs to have some way of describing what it wants, or have a way for us to tell it what the tasks are. And not only has it to like learn to act in new environments, but I also need to be able to solve various different tasks. And this made this problem extremely difficult. And you can also probably tell from the fact that we still don't have very good home robots on the market yet. So we are taking this as our angle, and that's actually exactly what we did in the work that I've focused on in my PhD. So these are some interesting examples of the kind of tasks that we want to enable our robots to do. So they can be very long horizon. So these are already considered very long horizon in robotics. In this particular task, it's trying to serve a cooked green block, which we also call broccoli. And in this particular following example, so the task is to make a cup of coffee with sugar. And then you can tell that it's sequenced up a lot of different actions together, like moving, scooping, and pouring. So all these things need to be somehow combined in a seamless way in order to complete those tasks. So I'm gonna structure this talk with three different aspects of building intelligence into the robots. We've just seen some examples of how they're deployed and how they can adapt to different environments and solve different tasks. And we're going to focus more on the pre-deployment stage, where we're trying to build in the knowledge or let it learn the tasks that it will probably encounter in the real world, and building its ability to generalize. So that's the goal here. Now, let's first look at this part of prior engineering. So how do we build in the knowledge? And I'm going to apply an even simpler example here to just explain the kind of knowledge that we're going to build in. So the most important one is actually the AI planning language. So how do we talk to the robots, right? Of course, like people might think, yeah, we can talk to them in natural language. But as a machine, it needs some structure. It needs some like backbone in order to understand what exactly the tasks are. So let's first look at some examples that actually enable these kind of behaviors. We built this environment called Kitchen 2D. It was actually done around like 2018. And the goal there is to create a flexible environment that a gripper robot, so the little yellow thing there, can move around in this 2D world and interact with like objects in the scene. And for the AI planning language, we want to keep interpretable so that like we as human experts can operate with them. And we also want to make it relatively like compositional so that the robot can use them in a flexible way to solve like different tasks. So this particular language that we used, I mean, actually we're using some new versions of it, but the underlying story are pretty similar. So this language is called strips. It's a language to describe planning problems. And it's composed of several different components. So I'm gonna explain at a very high level. Some details might not be correct, but I think it's good to just like simplify things and make sure we understand the relatively like bigger picture so that we don't get caught in details. So the components that we will talk about are the initial state, the goal state. So basically it's where we are right now and where we want to be. And it also has a set of actions. And when we are describing the set of actions, we're describing with some contracts. So when these actions are applicable, and once we take these actions, once the gripper takes these actions, what's going to happen? So here's a very simple example. Maybe it's already a little complicated, but let me explain. So for this particular action, it's called pick. I actually just directly like screenshotted a piece of code from the GitHub repo that we released. And for this action, it takes in some parameters, which are the continuous parameters and objects that it will involve when carrying out this particular pick action. So the parameters that are getting involved include the gripper itself, the pose of the gripper, so where exactly it is in the world. And we're specifically saying, okay, it's a pick for cup. So there involves an object called cup, and pose 2 describes the pose of the cup. And then for grasp and control, they each describe how the gripper is going to grasp the cup. So whether, actually I have an example with a cup here. So whether I grasp from top or things like that. And then control is more about like how much force I exert in order to pick it up. All right, let me drink some. So for the two parts, when applicable and what happens. the one applicable part is what we call the precondition, and then what happens is the effect. For the precondition, it involves several different conditions, so including can grasp, which is basically a true or false function that says with all these parameters, I can grasp the cup. And then some other preconditions include the fact that for the pose of the cup, the table is supporting it. So we want to make sure if I have a surface, like the cup isn't floating in the air. And there are some basic requirements, like the gripper is at the pose that we are specifying. The cup is at pose 2, and then the fact that the gripper right now is empty. So like if you imagine the gripper already picked up something, then of course it can't pick up another cup. And then for effects, it's almost like what we would describe when an action like pick would happen. So including that, yeah, the cup is picked with a certain grasp. The gripper can now move with the cup that it's grasping. The cup is no longer at pose 2 because like we already picked it up. And then the fact that the gripper is not empty. And finally, we have a cost. So you can think about it as, well, there are some costs like electricity cost when the gripper like exert force and pick something up. So that's the cost we also want to minimize when planning for planning to solve any kind of problems. Okay, so in strips, basically what we want to do is to use these descriptions of the actions to go from the initial state to a goal state. And so I thought it might be interesting to just like do a quick example. So imagine we have a set of actions, the pick, place, move, move while holding, so move while holding something, pour, push, scoop, stir. So these are the actions the gripper can take. And the initial state is involve 2 objects, a kettle and a cup. The kettle is empty, the cup has water, and both of them are on the table. And then our goal state is that the kettle has water, and then both of them are on the table. So imagine you're the robot gripper. How would you sequence these actions together? Any guess? Okay, looks like it's too hard.
You solve some kind of planning problem.
Yeah, so exactly. You solve a planning problem. How would you start, right? What would be the kind of plan that you would carry out? I'm just gonna give you some hint. Well, first we need to move to the cup location. It involves some like middle state of like, if we look at the initial state, goal state, we know that at some point the cup's water will be transferred to the kettle, and maybe that's a pouring action. So as we are thinking about how to compose these different actions together, it's basically what our planning program is trying to mimic. And eventually, what's going to happen is that it's going to sequence these set of actions together with the kind of objects that's involved in these actions and with specific control parameters. So for this simple example, it would be like one particular plan could be that it moves to the cup position, pick the cup and move while holding the cup to the kettle location, pour from the cup to the kettle, move holding it to another location because eventually we want the cup also be on the table, and then place the cup. Okay, so that's the kind of planning procedure that we want to mimic for our robots, and that's also exactly what's going on for our planning program to to like operate with these descriptions of actions. All right, so those are pretty high level. Let me pause here and see if anyone have questions. All right. Okay, so one of the detail that I'm kind of like just brushed through is how do we figure out these control parameters and all these like continuous parameters? So again, I just screenshotted one action description from our code base. And for this particular action, it's called, well, it's pouring. You will see why it has a -gp here. And it involves several different parameters that are very similar to the pick action that we've just seen. And in the precondition, there's a very important one called can_pour, which is this like true or false, like a function that returns either true or false. And it involves the parameters, including both the grasp, which is a continuous parameter, and the control, which is also a continuous parameter. And actually, pose and pose2 are also continuous parameters. So how do we figure these out, right? Given some of these parameters, we need to have a way to return whether can_pour is true. So we are going to do this with the score function, and it will help us to evaluate how good each control is. And given, so I'm like abstracting out a lot of parameters as the context. So given some context and the control parameter, we want our score function to be larger than a threshold to set can_pour to true, and otherwise it will be false. So in order to do this, well, we need to run some experiments. We need to collect data. So in the 2D world, it's relatively easy to like run these experiments because we just need to like specify the exact locations of these different cups and grippers and the control and simulate, right? So in this particular illustration of the score function, for each parameter theta, it will correspond to different sizes of the two cups, as well as different control parameters. So at which exact location do we grasp the cup? And also like how much do we tilt? So these will be the inputs theta that would decide what kind of score do we get. And the threshold that we're setting here is that the score should be greater than 0 in order for us to have a successful grasp, a successful pouring action. Okay, so these are getting more familiar to some of the folks here. So we are going to model the score function with the Gaussian process. And this is to make sure that we can actually design the experiments so that when we move to the real world, we don't have to like run a ton of experiments and eventually ended up spending a lot of time. So to do this, we look back into the literature and realize this is in fact simply a level set estimation problem. So for level set estimation, basically what we care about is to find out the high probability super level set. So it's the regions denoted by the black lines here. And these are the high probability super level set when we set the lower bound to be greater than a certain threshold. And so I'm just gonna like use an acquisition function that exists in the literature, which is called the straddle heuristic from Brian et al. In 2005. And for this particular heuristic or acquisition function, it has value if the mean is close to 0. So remember that we've set our threshold to 0. And then it also has high value if the variance is high. So we're going to just like use this particular acquisition function to decide where exactly do we sample our theta, and to decide like which kind of experiment do we run. And it's going to select the points that will gradually help us to reveal where the high probability super level set is. Okay, I forgot to explain, but this G function is our score function. And eventually, what we want is that a description of whether a point will give us a score greater than 0. And this is exactly what the level set estimation method helps us to do without querying, like without doing many experiments. So we tested, I think this is actually in the 2D example. So we run the particular GP level set estimation method against some neural network approaches as well as random sampling, and found that it's actually a lot more data efficient. Okay, so these are some of the examples in this particular 2D world where where we illustrate like what our final goals are, basically for very different locations or sizes of the objects in the world. We can use our gripper without changing anything in its program and let it generalize to these different circumstances, while changing also changing the goal. And you can see that with our AI planning language and the learned action, it's able to generalize both to the sizes of the objects as well as to like different arrangements. Both of these illustrations have the goal of, actually let me loop it. So both of these have the goal of serving a cup of coffee with cream and sugar on this green coaster. And it's actually really interesting to observe that it's trying to do things in very different order, but eventually reach the same goal. So in the top, it got the coffee first and then poured the milk. But in the bottom, it actually got the coffee and poured the sugar before moving it. And while preparing for the location of the coaster, it moved the cup and tries to pour the milk in the bottom one. But eventually, what they're trying to do are both to serve this coffee that has been mixed with cream and sugar. Okay, I hope this is entertaining. We're gonna finish this and proceed to the actual real world environment. All right. So let's think about how all of these that I described happen in the real physical world, which becomes a lot more complicated. So this is our system when trying to design this, these experiments in the actual physical world that involves a robot and realistic objects like bowls, spoons, cups, and also like things that we want to pour or scoop. So the left of the slide is illustrating the kind of objects that we're going to interact with, and then the right-hand side is the modularized system that we use to design our to basically design our experiments and carry out the execution as well as score the results. It might look very complicated, but we are going to explain like one section by one section. So we call this particular system LTEMP because it stands for Learning and Task and Motion Planning, since it involves the learning component as well as the planning component that acts both on the task level and on the motion level. All right, so let's decompose it to understand a bit better. In our 3D physical world, we don't really have direct access to locations or poses of these objects. So we need a perception system. And in our particular perception system, we basically wanted to give us an estimate of what our current state is. whenever like we're in the process of executing the plan. And remember that in the strips language, we actually need to know what the initial state is and what the goal state is. So the goal state can be like described by some human, but the initial state need to be figured out before we do any planning. And the way we're doing this is to use a visual object detection system to first look at the table and then figure out what the objects are. So like getting the labels and bounding boxes for all of these objects. And once we have these bounding boxes, we take out the point cloud that's being received from our robot and use the bounding box to crop out the objects that crop out the point clouds that correspond to the objects. And then we access the models corresponding to these specific objects and try to reconstruct them with the point cloud. So, well, all of this sounds pretty complicated, but the goal is really to reconstruct what the scene is in the robot's belief. So once we have that, we get the initial state, and we can use it to decide how to get to the goal. And in terms of our experimental design, basically the goal is to execute a certain action with the parameters specified by the learning mechanism. So all the GPs and straddle approaches that we've seen earlier. So that's what this particular learning module is doing. It tries to output a theta, which might involve both the context, so the sizes of the ball, and the exact control parameters we will take. And it's going to send to the planning module so that the planner knows, okay, this is the kind of experiment that we are trying to run. And it's going to coordinate like every components of the robot and tries to see, okay, where shall I move to pick up the cup and then reach a particular position and carry out the action. And we did this for 2 actions. One is pouring and one is scooping. So in the execution section, we need to execute the plan and score the control parameters output by the learner. And we, so at the time, just decided, okay, this needs to be done, but how do we do this, right? We don't want some grad student look at how many beads are poured into the cup. So we just got 2 kitchen scales and use it to score, okay, how many things are being poured to the right location. So those are the kitchen scales connected to our system. Okay, to give you some examples on what I've talked about so far, these are the experiments the robots are doing. Because it's not going to take a lot of trials, so we just decided, okay, forget about the automatic system. We'll just have grad students doing supervising the robot and tries to make sure it does the right thing without ruining our lab. Yeah, so these are the kind of experimental design and execution process. And we collected data and looked at the comparison to random sampling. So the active sampling corresponds to the level set approach, and the random sampling corresponds to just uniformly random sampling in the world. And both of them use a GP to do the classification task. So we eventually look at the F1 score on the test set. So the test set basically includes different sizes of the objects that the robot has never seen before. And the generalization results are actually showing that active sampling is much better than random sampling, which is what we want, right? A lot more data efficiency, so we don't have to do too many experiments in the real world. All right, so here's a little behind the scene, because we need to figure out what exactly is the kind of GP that we're working with. And the tricky part is in these kind of robotic experiments, because we represented our tasks with the parameters, including like the position of the like objects that are on the surface. So you can imagine, like if I shift my cup a little bit to the left or right, the actions we'll take will have very different results. So like maybe the first action I take at that particular position is that I put everything into the cup. But then if I shift it a little bit, suddenly nothing is poured. So it's very discontinuous. So we want to make sure our GP can capture that. So it turns out like for a Gaussian process with the multi-layer perceptron, kernel does slightly better in these circumstances. Okay, so we've talked about the before deployment. So how do we build in the knowledge of the AI planning algorithm? How do we build in the belief like a Gaussian process? And then eventually carry out the skill learning part by experimental design. So once all these are finished, just to recap, we want to deploy the robot in the real world. So, I mean, the experiments are already done in real world, but what I meant is like deploy it in a situation where it has never seen before and see how it adapts to both new situations as well as new tasks. And these tasks could have much longer horizon than just the pouring or scooping or picking up. Okay, so just want to show you, okay, these are done. Want to show you some results. All right, I'm gonna do some loop to make sure it doesn't end too soon. Okay, so these are a few examples. They correspond to either different positions of all these objects or number of objects in the scene or different goals. So I think the top goal is that I need to serve this white cup on this purple block with some like liquid in it. And because the objects in the scene are like organized in a very different way, so they're placed in different locations, so the planner will decide to do things slightly differently. So in the left hand side of the top one, it decided to move the cup first before pouring, while on the right hand side of the top row, it decided to pour first and then move the cup. So for the bottom one, the situation are also quite different. So we are trying to mimic a kitchen scene, and of course, like it's very dangerous to put the robot actually in the kitchen. So we're like constructing this lab environment to mimic that kind of situation. And in these cases, because the robot is able to just perceive, okay, what the initial state is, what the goal states are, and even if there are like obstacles in the middle, it's able to just detect, okay, I need to move away this green block first before proceeding to accomplishing my goal. And that's what it did. Like, we don't need to change anything else in this particular block. We don't need to build in more actions. It's operating with the same piece of program, with the same learned models, and it's able to generalize to a wide variety of environments and also tasks. All right, I'll pause here to see if there are any questions so far.
When you say that the robot learned to move different objects in order to achieve its goal via the same code, how far did you take testing of that sort of behavior? Did you change, how much could you change the environment and the robot would still be able to move different pieces around?
Yeah, good question. Thank you, Will. So it's actually, so these kind of behaviors are a result of combining the learning components where the experiments that it's carried out in the real world plays a part. So the data plays a part in the learning algorithm. And this, so together with that and a planning approach, which is just like the AI language that we build in, the kind of actions that we write, it's going to like show, so what it's trying to do is that it uses the learned components which exist in the actions and look at all the actions we have so that it can use the planning approach to decide how do we sequence it up together so that it can accomplish a very long horizon goal. So it's not trying to learn whether to move these objects, but rather it sees that, okay, if I need to use this particular scale of pouring, but something's in the way, then the planning mechanism gets activated and tries to make sure these obstacles are moved away before carrying out the kind of actions that will be critical for accomplishing the task.
Hey, I have a couple of questions. Thank you so far. One is, have you guys done much like edge case testing? So for example, like, what if you hid the cup in a bunch of blocks, you know, so it's harder to see or something like that, or like put it like teetering on the table or something like that to make sure it didn't push it off or something, you know, like some edge cases there. Have you done much of that?
Yeah, that's a great question. So this particular system, let me move back. So this like learning and task planning, task and motion plan system will rely on all the components being very good, and the edge cases that involve like screwing up the perception will directly result in like having a wrong initial estimate of what the state is in. And yeah, it's it's not gonna do well in those situations. But if someone like who's familiar with like robot learning or these kind of tasks in general, you will realize that everything I've talked about so far is assuming deterministic systems, and so it doesn't. There's no real stochasticity, and all the states are fully observable. So we're actually assuming that the perception will always give us the correct state, which is of course not true if you're in this like really messy kitchen and trying to figure out, oh, something's behind like a piece of cloth, or the spatula is hidden in a drawer. So it's not going to be able to do that. But there are a lot of research going on to make sure these kind of capabilities can be embedded in the same system.
Oh, thanks. The other question I have is, have you guys started to do any operation constraints, like don't touch that or don't move this or something like that, you know?
Oh, I see. Yeah, interesting. So you can put it in the description of the goal state. So make sure that, yeah, you will never move this particular thing, and add it as a constraint so that when the planning method is trying to figure out how to sequence actions together, it's doing like it's making sure that these constraints are satisfied.
Thank you.
Yeah, thank you. Okay. Any other questions before I move on? All right, I'll continue. So a last piece of puzzle is, how do we make sure the prior engineering part carried out by our experts will be informative enough for the robot to like decide what to do in the world? So in this case, we can actually group the second two components together because both of them or acting in the stage of doing Bayesian reasoning, deciding what to do, and basically build on top of the priors assigned by our experts, and to act intelligently both in experimental design and when adapting its behaviors in the wild. Okay, so if we think about this problem a bit more carefully, basically what we want to do is to make sure the experts' belief, which are described in very abstract terms, like we don't really think very quantitatively, but the kind of priors or the probabilities, the belief that the robot operates with, they're numbers. And how do we make sure they're aligned? So that's the problem that I call the Bayesian alignment problem. If we really want to develop an intelligent system that at every stage it will carry out the kind of same behavior, if we were to do it, then we need that initial alignment. So, and it's really hard, right? So in our more recent work, we're looking at this problem in a more principled way. So this is the kind of high-level picture that we are using to understand this particular problem better. So instead of having a very complex world and various very complex tasks, we're abstracting everything out and just say, okay, what's the most compact decision, like sequential decision-making scenario, such that we can think about this alignment problem a lot better. And basically, here's the diagram. So we have an engineer or expert who builds in the knowledge to the robot, which the robot will interpret as the prior. And then it starts to interact with some kind of black box. It gives out query, it collects data. And the goal here is to make sure we can translate that expert beliefs into more quantitative priors that the robot can operate with. So if we want to build this particular system out, like the kind of initial belief that's most easy to operate with, well, in my view, it's a Gaussian process, because it's relatively cheap to update its beliefs, well, comparing to much more complicated models, and it has a closed form posterior prediction where we also get the uncertainty prediction for free. And technically, it also has much larger model capacity than deep learning models, because it's modeling a distribution of our functions instead of a single one. Okay, so then the question for the expert is, which kind of prior do I choose? Do I use like a very smooth one as the kind of GP prior we assign to the robot, or do we use like a very weakly one? And without knowing a lot about what this new functions that the robot is going to encounter in the future, it's very difficult to make that decision, right? Like as the experts here. And even if we kind of know what's going on with the tasks that the robot will encounter, it's very hard for us to think in a quantitative way and decide, okay, let's assign 0.1 to the length scale. That's simply like very hard. And the thing is, Gaussian processes, like it's a very wide family. You can initiate a Gaussian process with almost any kinds of mean and kernel functions, as long as the kernel is positive definite. So here are some examples. One thing to note is that in the top row, if you look at the mean function and confidence intervals, they look exactly the same. So while they look the same, the behaviors of the functions, so the kind of characteristics of these functions generated from the three Gaussian processes are very different. And then if you look at the bottom row, we can also have very flexible mean functions. It can really be anything. And we And once we like generate the functions from these Gaussian processes, it will respect that the mean is at this position. So the functions that I'm generating will have a mean that is specified the mean function of the GP. Now, how do we select, right? It's really too difficult for a human mind to comprehend. And the way that we decided to think about this is that let's consider where that expert belief comes from. And if you think about that question, well, our beliefs come from experience. So it comes from the experience with relevant tasks that we had before. And those will form our underlying belief about the kind of tasks that the robot might encounter. And if we describe those tasks with the kind of underlying functions and that's like behind each of the tasks that we had experience with, we can basically visualize them in a way. I mean, we don't really need to visualize. We just need to point out, okay, here's the data related to the these experiments, these like previous tasks that we had certain experience with. And our goal here is, how do we make sure we can take those data that the expert pointed out and translate into a prior, a Bayesian prior that the robot can operate with, such that the prior is aligned with the expert's belief. Okay, so that's our goal. And we can do this by learning from these kind of training functions. We can also reframe the problem as, how do we generate new functions that mimic the characteristics of the functions for these observed tasks? And this turns out to be a pre-training problem. So basically, we want to train our Gaussian process so that it generates functions that look more and more similar to the ones that we had experience with, so the training functions. And okay, I'm just looking at the animations. It's always fun to watch. So for this particular pre-training methods, we are so the way we're thinking about it is, let's look at KL divergence between the underlying ground truth, so what the expert belief is, and the model. So we want to minimize the KL divergence between the ground truth and the Bayesian prior that we are going to assign to the robot. And in this particular paper, pre-trained Gaussian processes, I think we're for Bayesian optimization. So we developed several different variants of objectives so that we can minimize that KL divergence. And eventually, yeah, like you're seeing here, even if like the Gaussian process is generating like functions that are very different in the beginning, it is able to gradually find its way to generate functions that both agree on the mean level and also like mimic the kind of variations on like, which is something that we may think about in terms of length scales. So the nice thing about it is that with the pre-trained GP, now we can have much better epistemic uncertainties so that we can use it to make decisions. So here are some comparisons. On the right-hand side, we have a Gaussian process with a hand-specified prior on the length scale and I think the signal variance of a Gaussian process with square exponential kernels. And on the left-hand side, it's a pre-trained GP that we also use a square exponential kernel, but with some encoded inputs with like a neural network. So we try to like make our search space for the mean function and the kernel function very flexible so that we can get a Gaussian process that is as close to our training functions as possible. So for these two different scenarios, if we set the observations to be at the same place, actually what you can see is on the right-hand side, it's very difficult for this GP to capture what the test function, so the orange one, is by looking at very few data points. But for our pre-trained GP, because it has information to past experience, so the training functions, it's able to like model the test function in a much more calibrated way. And then the same thing happens once we have more observations. And with 3 observations for our Gaussian process on the right-hand side, it's already been like pretty confident that, okay, I kind of know what the test function is. But then on the left-hand side, it still have a lot of uncertainty because it knows that, yeah, the function is a lot more wiggly than than the kind of assumption that we make on the right-hand side. Okay, so this seems pretty obvious, but see, I only have 5 minutes here. The kind of idea is really about we need to make sure we get the right alignment between the underlying expert belief and the Gaussian process prior that we assign to the robots to make decisions in the world. So pre-training gets you better alignment and eventually gets you much better decisions. All right, so here's a summary. We talked about how to think about like domain expertise, the role of domain expertise in this in this process of embedding intelligence to competent robots. And we also talked about how we can build on top of all the priors that we engineered to the robot and do experimental design, and combining the knowledge from the from experimental design as well as the domain expertise that are like, you can think about it as the AI planning algorithm, AI planning language, as well as the structures we build in and the Bayesian beliefs, we can get very awesome robots. So thank you. And although I don't work on robotics anymore, I hope you can, still like, even if you don't work on robotics, you can still take away some interesting lessons and build your own intelligent systems. All right, questions?
I have a question. In this pre-training, when you try to match, as you said, KL between the data and the prior, right? You said something like this, right? And I wonder,
yeah,
what
so
is like the technically really happening there, right? Like you have to calculate KL between 2 random variables, maybe between 2 random stochastic processes. That is also possible, but I'm not 100% sure. I understand how can you calculate it between a prior. So I'm sure that there's a way. I just wanted to hear a bit more details on this.
Yeah, absolutely. I don't know if I have slides for that. Wait a second.
So one thing I'm wondering is whether you have in the end a parametric optimization problem, or there is a way to learn a non-parametric prior. This is what.
That's a really great question. So we are making the framework relatively flexible. So we're abstracting away about like what the search spaces are for the main function and kernel function. You can even do like discrete search if you just have like a few options for the main function. But in our case, we're trying to make the function space for main and kernel as flexible as possible so that it can fit the data with more capacity. And let me find the paper. It might be easier to just like explain with the equations. Right, I don't know why it's loading so slowly. All right. Oh, I can't believe this is taking such a long time to load.
Suspense.
All right, here we go. Okay, KL divergence. Okay, here it is. So we are formulating it as the KL divergence between, let me make it larger, between the ground truth Gaussian process, which obviously we don't have access to. But it's like we're just trying to think like what the underlying problem is. So the KL divergence between the ground.
So the optimization problem is then over. So you need to kind of create a discretization, I guess, where you take this supremum, right?
Right, because we, I mean, obviously we can't have access to all the inputs that exist in a continuous space. We only have this free one.
And you discretize on X.
So
because you could also create kind of like a finite basis, like, I don't know, random Fourier features and these things, and also optimizing that space. So I wonder whether so it's discretization on X or on some other basis.
Yeah, so there are quite a few approximation steps that we took. First, yes, you need to have a finite X, because otherwise we can't really compute it. And second, we need to somehow approximate the underlying ground truth with data. And once we have that final approximation, only till then we can think about, okay, what kind of search space do we use for our model, which has like either a parameterized or some finite set of like mean function and kernel function and noise variance to eventually make sure these two models are aligned.
But yeah, I think this answered my question. These equations.
Yeah, sure. I have to. Thank you.
Thank you.
I had a quick question. I just first wanted to say that I think the whole idea of using pre-training to capture rich prior information about the world is a really promising direction. So I think that's very very cool. But I don't have a specific question there. I think this method all makes sense for all the level set stuff you were talking about. I just wanted to clarify: were you using that straddle heuristic acquisition function for all of that?
For all of the experimental design?
Yeah, for the level set estimation part of it in particular.
Yes, we are using that. And actually, you can use anything. But we just decided to use this because we're already really drained by all the robotic setups.
Oh yeah. I was basically gonna ask. It seems like you get a big bump over being intelligent here versus random search, right? In some of these earlier plots you were showing. I was wondering if you think, or if you did any experiments in this study when you were working on this stuff, as to whether different level set acquisition functions had different types of performance, like if it was sensitive to this, or if you just mostly stuck with that choice and didn't play too much around with other choices for the details here.
I see. If I remember correctly, we did play around with some level set estimation approaches, but this one seems to be pretty robust.
Yeah. Okay.
We just said, yeah, let's use the straddle heuristics, and it's also very easy to interpret and easy to construct.
Got it. Thanks.
But I think like there are probably people here with like much better level set estimation methods. So I don't want to say like, oh, this is the best methods we tried. It's just like we tried a very few amount of them. Like we tried a few strategies and then realized, yeah, this is pretty good, and then we just like used it.
I think I remember that, yeah, this heuristic doing pretty well for some stuff that I and some others have done too in the past. So yeah, agreed with you there. But I am interested in, yeah, its sensitivity to this choice.
Yeah, cool. Right. It's very, I think sometimes it's pretty hard to say, because it depends on what kind of functions that we're trying to derive the level set.
Yeah.
And this just happened to become a good choice for our problem.
Got it.